Hi, everybody. Welcome to our next round of IRIS-HEP fellow presentations. Today we have Ajay and Jason who are going to present.
Hey, I'm Ajay. I'm an IRIS-HEP fellow for the summer 2021. I'm from the University of Washington, Seattle. And my project was about integrating REANA into ROP. I'm sure you won't, let me just describe these terms for you. REANA is it's a cloud platform where you can run analysis and reproduce them. And ROP is stand for Reproducible Open Benchmark platform where you can, that's a project I was working on, where we create, we define a task and have a workflow that benchmarks different submissions and rank them. So let's start with ROP first. Let me just describe it in a brief way. It's like if you can think of like something like Kaggle, it's something similar, but for developed just for workflows where you have a task defined and you have some benchmarks that you want to calculate, and the users can submit their workflows, and they ROP would benchmark them and rank them. And the main important task of ROP is that these results should be able to be reproduced easily. The inspiration for ROP came from the top tiger comparison analysis. You can find the paper here. I think it's titled A Machine Learning Landscape of Top Tigers. Top Tiger is a model that works on data produced by particle jets, and classifies those jets as either top cog or like background QC radiation. So that's what a top tiger is, and there are different architectures for it. Like you can see it, CNN is over here. It's like convolutional networks, and you have all these different models, and they have different AUCs and accuracies. AUCs being the area under the ROC curve. These are all the ROC curves for all of different models. Um, and to briefly go over this, the main task over here was to benchmark these. These were the benchmark that were produced, and benchmark them on the same data set. That was one of the main part of it, and it was supposed to be reproducible easily. And the way they did it was using Jupyter notebooks, but the problem arises when everyone had to have different dependencies installed onto reproducible results. That's where ROP was designed, with the two main goals that it should be easier to just have something like a task defined, like a simple task, like this is a data set, and you have to classify them, or like regression tasks or something like that, and have a benchmark associated with those tasks. And users should be able to just give their workflows, and it should be able to reproduce them. That's how ROP was designed to be. And right now, so my goal was focus. This is just a brief. Sorry, this is just a brief description of ROP, where there are like 3 layers to ROP. User interface, which is just a way to interact with ROP. Like it could be like a command line interface where you type commands, or like a web interface. The flow sub is the main part of the ROP that is responsible for taking the user input and running the different workflows on a server and ranking them. It's kind of like the main backend of the ROP. And a workflow engine, which again, it's like an environment where you can run a workflow or any process in general. So just to clear some things out, benchmarking just creating some analytics from, or having some defined way to rank all of these different submissions. Most of the times in ML models, we use accuracy, or like an area under the ROC curve. And ROP is most of the tests that we run on ROP was mainly these 2 benchmarks. So this is kind of where REANA comes in. I think I skipped the slide here. Oh yeah, this one. This is the top. This is a view of ROP, where you have a front end, a back end, and a workflow engine. So my project was based on REANA. So REANA is a cloud platform that's used to run like Docker containers or any containerized workflows. And a REANA server would, it could run your workflow, and the main part of it, it's going to archive it for other people can see and to run them easily. And my job was integrating this REANA API, REANA service into the ROB. So the ROB is not limited by the server it's running on. It can run it on a REANA server. A REANA workflow typically looks like this. We include a version just to be consistent with it, but main parts are the inputs, workflows, and the outputs. The inputs are either input files, like these are the files, like a hello world, like a Python file and data set, and the different parameters. So in REANA, you can have a parameterized workflow. So a good example would be when we're doing any machine learning kind of stuff, we can define these to be hyperparameters. And let's say if you want to do hyperparameter optimization, you can just change these parameters in the file and run REANA multiple times, so that we can then compare them. So and we can optimize hyperparameters. The other part is a workflow. That's the main part of the REANA, where you would have an environment where you want to run this workflow in, and different steps can have different environments, and the command that you want to run. Lastly, we have an output file. Those were reproduced that you can download later, and these would contain our benchmarks in the context of ROB. This file is typically in a YAML format. So to use a REANA cluster, you need a way to access token for that specific cluster. So on REANA, originally is developed by CERN, but it's not limited. You can deploy your own REANA server, and that's what we did for our testing right now. So if we right now, sometimes the CERN REANA cluster is kind of has a lot of workflows coming in, so you have to wait a day to see if your workflow even works, even though it might be a really small workflow. You have to wait like a day or two sometimes to see if your workflow is correct. In that case, we just have we deploy our own REANA cluster, and you can have managed that. And you see the server URL and the token to run anything on REANA. And we integrated a Python package into ROB. There are like a few simple steps to run a REANA workflow on ROB. That's what integrating was to first create a workflow, was to first convert the YAML file into JSON, and then contact the REANA server to create a workflow for it. The next step was uploading all the input files to the server, and then starting the workflow. The other task was to monitor the workflow. So let's say the time intervals, we can pull the server at like every 10 seconds to see when the workflow has finished. And we then download the execution. There are a couple of benefits for integrating REANA into ROB. One thing is the archiving of a workflow. In this case, where everything that you need to reproduce results is already archived on a REANA server. This includes all the input files, the workflow that we use, like the Docker environments and their commands, and also it also contains the logs. So you can, if let's say later in the reproduce you get an error, you can look at the logs and compare them to see where it's going wrong. And the last one is the output files that you can check to see if your reproduce workflow is correct or not. The other task is that the ROB is no longer limited by the server it's running on. So if you're running ROB on your local machine, and let's say your task is pretty heavy, like you require a lot of computational resources, you're not limited by your laptop. You can have a remote REANA server where you can contact, where you can submit, where you can run these workflow and then benchmark them locally on your ROB. And the last part is where ROB can just run multiple submissions at a time, and this would result in faster benchmarking. That was my presentation. Thank you.
Thank you, Ajay. Anybody have any questions? No questions? All right. Again, thank you again, AJ. Next up, we have Jason, who was mentored by Daniel and Savannah. Savannah, you want to say a few words about Jason's work?
Jason worked on a project enforcing Lorentz invariance in graph neural networks for jet tagging. So graph neural networks, as we've seen through this fellowship program and a lot of other work in IRIS and other places, have found a lot of applications in particle physics, particularly in reconstruction tasks like tracking or clustering or flavor tagging. So in this work, Jason explored if there are ways to improve the performance of networks or make them smaller by enforcing symmetries that we expect to exist in physics data. So in particular, he focused on enforcing Lorentz invariance in these kind of networks for the task of jet flavor tagging. So he did really excellent work over the summer, and I'm excited for everyone to see his presentation. And I really enjoyed working with him, and I think Daniel did too. And Daniel, if there's anything you want to add.
You nailed it.
Great, thanks.
Yeah, so as Savannah mentioned, the research I did for IRIS-HEP this summer was on the Lorentz equivariance or jet tagging. And so the jet tagging problem is essentially, if in the particle collider experiment, when you collide the particles together, what ends up happening is that once they collide, they produce a lot of jets, which all have different momenta. And so the whole idea here is that once you are able to keep track of all those particles that are all collated together, you want to be able to determine which particle that constituted originally. And so the whole problem here is you're given a lot of momenta, and you are to classify whether it's a top quark or a light quark / gluon. And so for now, we have a public data set that's the simulation, which has 1.2 million jets for training and 400,000 for validation. In the whole experiment that we ended up doing for this summer, we ended up not being able to have enough time to train the whole entire network. So we ended up using a smaller subset of 100,000 jets for training. And so there are many other models that also deal with this jet tagging problem. And so one of the main ones is ParticleNet. That one uses about 500,000 parameters. It's an edge convolution graph neural network, which has permutation variance because it's a graph neural network. And then the other main network we're going to be talking about is the LGN network. That's called the Lorentz group network, which it uses a lot of group theory to take the tensor products of a bunch of irreduced representations of the Lorentz group to produce higher order tensors, and then decomposes it using the Clebsch-Gordon coefficients so that we are able to obtain the nonlinearity for the network so we can train it. And so the reason why we want to work on this work and create another network is because the whole problem is that we want to, in the machine learning framework, we want to start reducing the amount of time it takes to train a network, and also reduce the amount of memory it takes to just run the network, just having all the parameters in the network. And so, like I said before, the ParticleNet network that has 500,000 parameters, it turns out that the LGN network only has about 5,000 parameters, so it has about 100 times fewer parameters, yet it achieves within 1% the same performance as ParticleNet. And so the whole idea here is to do a similar thing and use the symmetry that we know. So we know that there's the Lorentz symmetry in just general everyday life. So for these jet simulations, the whole idea is that you can have a reference frame that's viewing the particle experiment, but you can also transform into any other reference frame using a Lorentz transformation and just still obtain the same answer. So that's what the whole idea here is with node and edge equivariance and also permutation invariance. So equivariance is what achieves the special property. So if we have a neural network, which we represent by phi, and we take an input, so let's just, for now, just stay in the Euclidean space. So it's just rotations that we were dealing with. So if we take a generic, I guess, 3 vector, so just just a location space that points in some direction. So what we want is that once you pass that through the network, we also get the same answer if we rotated it before we pass it through the network. So if we have a rotated version of that vector, we pass it through the network. That's the same thing as if we had put the original vector through the network and then rotated it afterwards. And so this makes it so then after we pass through the network, we can do some, we end up with another vector. So we end up with another 3 vector, and then we can do some invariant operation that, for example, if we have the 3 vector, we can take its norm, and that gives us an invariant quantity in the Euclidean space. And so that's the whole idea of the network, since then if you rotate the input at all, which is the whole idea, then it doesn't matter what happens at the end because you end up reducing that rotation by taking the norm anyways. And so for Lorentz equivariance, that it's not the same, it's not the perfect analog to the Euclidean group. The Euclidean group includes rotations and translations, but the Lorentz group is only the rotations and boosts and not translations. The Poincare group includes the translations. And so the main model that we based our research on is the EN equivariant model, which is called EGNN. And so so that includes the rotations and translations. So the idea of this network is that we take the difference between 2 vectors, so 2 of our inputs. So what that gives us is a translation invariant operation. Since if you subtract 2 vectors, it doesn't rely on the absolute position in space, since we're subtracting off that relative quantity. And so the other thing is to make it rotation equivariant. We take the norms of the vectors to act as our hidden feature nodes throughout the operation. And then once we create these invariants, we can use an MLP on them. So we can pass them through any neural network that we want. And it'll still be invariant since it's just a neural network being passed through. And so that's how we're able to achieve all of our nonlinearities using the invariants. And then we have an update for the vectors themselves so that we still obtain equivariance. And so the whole concept of this comes from simply just, if we have 2 vectors, so in our whole jet tagging experiment, we have up to 200 different 4 momenta. So the idea here is you can add them together and you still obtain a four vector. And you can also take their linear combination, so you can multiply them by any scalar and you still get a 4 vector. And so that's the whole idea here, because if we want the input and the output to both be 4 vectors, we just need to make sure that we're only taking linear combinations to them. Since if we were to say multiply 2 4 vectors together, that's like taking the tensor product and we obtain a 2-dimensional tensor, which doesn't transform the same as a 4 vector anymore. And so that's the whole idea here. We want to take linear combinations of 4 vectors in the update, and then we use the Minkowski norm instead of the Euclidean norm throughout the model. And here's what the model looks like. So the main thing here is that we have the messages, which is labeled by M, which are invariant. It's labeled by a vector symbol because it's essentially, it's just an array. And it's the same thing with the feature vectors that's labeled by H on the bottom. So all those are invariant quantities, while we have this one equivariant 4 vector update. So if we look through that update, the next layer is equal to the same, it's equal to the same thing as itself, plus an extra term, which is a linear combination of different 4 vectors. And then that's multiplied by an invariant quantity. So that's one of the MLPs labeled by phi x, which is a function of the messages, which is also invariant. So the whole idea here is to make sure that everything else except the 4 vectors are invariant quantities. Yeah. And so this is what the network looks like in a more pictorial format. So we have the inputs. So that's all of our 4 momenta. And then we want to calculate our invariant embeddings. So we calculate all of their norms. And then since all those are invariant quantities, we're good to go. So we pass that through the network so we compute the messages. So after we go through the messages, which is an MLP, we take their aggregate. And so once we aggregate them, we can just do the standard graph neural network stuff. So the only difference is the vector updates, which is labeled by phi p and the pi l+1. So that one is the same equation as last time. So when you actually train the model, so as I said before, we're not able to train it with the 1.2 million parameters as many of these other networks are able to. So we ended up not being able to, we also ended up being able to test for a lot more epochs than the other networks. So for LGN, they only trained for 50 epochs. But the difference is that their model took 7.5 hours for each epoch. While for our network, we ended up being able to train each epoch for about a little over 30 minutes. And so it ends up being that if you try to estimate the time difference for training, this LEGNN network should train about 12 times faster. And so you can really see here that, yeah, the particle net model ends up having way more parameters than the other models, except for ResNext. And so one of the issues here is that when we ended up training the model, we ended up making an error in the code. And so instead of the, I can go back. So when we're going over here and we're initializing the feature vectors, we're taking the absolute norms of the 4 vectors, but we ended up taking their differences over here and then put that into this network over here, which ended up requiring 2 indices rather than 1, which ended up messing with the network a lot. So it ended up pretty much being invalid through the network. So we ended up only having the 4 vectors training rather than the feature vectors. So we're still able to obtain about almost 92% with this, but Dr. Daniel Murnane did some quick testing and was able to achieve about 94% accuracy with the fixed model using the absolute norms. And so one of the other important things is that when we were going through deciding what kind of network we wanted to do, we looked at the LGN network and we're looking at generalizing that. But we ended up finding that once we found the EGNN network and we decided to like, hey, look, we can generalize this to the Lorentz group. We ended up making comparison between the two, and we found that the EGNN network is actually just a subset of the LGN network. So that there's an appendix at the end of the presentation, but I don't think we have enough time to go over that, but it's there for people who want to look at that. And so the last test that we did was just taking just a randomized network and then just putting through a bunch of different 4 vectors through with random Lorentz factors up to 10 to the 4th. And so the whole idea here was just to test how well the network held equivariance, since the whole idea was we constrain the network in the first place, so then it is equivariant. And so this is the results we obtained, which are pretty good. And so that's pretty much the LEGNN network. I just wanted to end with the conclusion that about the whole IRIS-HEP program. It was a great experience. I went through a lot of parts of the research process and was able to use a lot of physics and math to apply it to a machine learning model, which is mainly what I want to get out of this IRIS-HEP program. And so I'm glad that I was able to have the opportunity to participate in this.
Oh, thank you, Jason. Any questions for Jason?
Yeah, I just had one. This is a very interesting talk, and I was curious if the training or the data set that you had had any pileup in it, or just other extraneous particles.
You mean like for the classification?
Right. If it was only jets, yeah, for the classification.
Yeah, it was only jets. Okay. So I also have references at the end of here. So this is the public data set that we used. But yeah, it only contains jets.
Okay, thank you.
Mm-hmm. Any other questions?
All right. Thank you everybody for coming. Thank you to Jason and Ajay for your presentations, and thank you to the mentors. We have another round of talks coming up next week, so be on the lookout for those. Thanks everybody. Bye.